Everybody ready? So welcome to this week's Icon Seminar. It's a pleasure to have Professor Rama Yedavalli, one of our alumni. He's currently president, well, he's an academy professor at Iowa State, and then recently he started a startup company, which is called Robust Engineering Systems. He graduated from the Department of Engineering. Prior to that, he was in science in Bangalore. He's received many awards, fellow ASME, IEEE, AAPS, Social Fellow at the IEEE. He's also received the Schur Award for Best Paper on the Alumni Research Award. 2001. 2001, published nearly 200 papers. Which we're using in our eigenvalue course. And like I said, he's currently an academic professor at Fall State. But
thank you, Martin, for your generous introduction. Good evening, everyone. Again, thank you very much for all of you being here on a Friday afternoon, which is very difficult for you to pay attention to some academic stuff like this. But I'm, again, really happy to be here. And as Martin introduced it to you, I myself am an alumnus of Purdue University. Again, back in those days. So I don't want to tell you which years I think. I don't want you to know my age. But I think he also mentioned. But again, happy to be here. And this has been a while since I came to visit Purdue. Back in, I think about 15 years back, I was here to give a regular seminar at the Department of School of Aeronautics. So again, after such a long time, it's nice to be back here. And this time, of course, I'm kind of here in a kind of a different role, kind of a little unusual, I should say, for various reasons. The first one is, as you can see, on one side, I'm acting like a professor. I'm an academic professor at Hurwitz University, where I have been there for the last 35 years. And now, but this time, I'm also acting like an entrepreneur. As you can see, I have my startup here, Robust Engineering Systems. And I deliberately actually became an emeritus to concentrate more on the RES. I'll keep calling it RES, Robust Engineering Systems. Fortunately, because I started this dual role after I became an emeritus, I want all of you to note that I can don both caps with no conflict of interest. So this dual role, it has no conflict of interest. That is good to know, because sometimes when I kind of in a way make some provocative statements in this seminar, I'm conflicting my own thing. Type of thing. I did a lot of research in the so-called eigenvalue-based control theory, and suddenly now we'll talk about a new stability concept called convex stability. Before I start the formal presentation, first of all, I want to thank immensely the ICON seminar committee members, especially Martin, Shreyas, Ziran, all of those who I met today. Again, thanks for arranging this seminar for me, which is a very good platform to kind of convey my message, which hopefully will be useful to all of us here to expand our knowledge base and do exciting collaborative research later on. So as a professor, I'm available as a faculty member to do some research proposals. Again, even if as an entrepreneur, some private industries can look into what we are doing and encourage new research. So with that, a couple of key statements or phrases we need to catch right here in this first slide. Convex stability. So in a way, that is currently new word, Hurwitz stability, Schur stability, Lyapunov stability, sample data system stability. We are familiar with all those age-old, very powerful techniques for a long time. But now we are coming up with a new stability definition, which I'm now calling convex stability. And then distributed actuation and sensing. Those are also, again, maybe not new words, but the way I use it, when I say I, my RES or, yeah, pardon me if I'm saying I many times, because most of this is my own kind of research. I didn't have any graduate students to help out in this part of convex stability. But before this, in my active life, I had mentored a lot of graduate students. I hope very happy about that. So those are the key phrases we had to catch here. Pressing the next slide. Is that something I do here? Or is there any pointer that I can use? So I press here.
Just press.
There. Okay, yeah, excellent. Yeah, thanks. So what I'll do is I'll take about 50 minutes. It's already started here. About 50 minutes, and then try to kind of keep it as timely as possible. So let me spend one slide on what I was doing in my pre-Emeritus slide. Then, as I said, we'll talk about why I'm excited about this new toolbox we are talking about, and then spend a few slides on why suddenly I'm saying some of the kind of linear algebra methods. I mean, we kind of go away from them and then do something new, and then actually introduce some superior properties of this so-called new toolbox. And then in the end, yes, it is. Yeah, excellent. Thank you, sir. It is my urge, and then to kind of express my desire to collaborate with all of you young minds. We have so many new things to do after you understand what why this is all very important. No, that's okay. No, I can manage. That's so yeah.
Advance the slides. Just push.
Right. Yeah. Okay, next. Yeah. Okay. So let me say if you have one slide about what I have been doing in my Emeritus, the Emeritus. So this slide is only to simply show you that during my active days, I hope for some of you, maybe Martin knows about it. We have been very active with the robust control of dynamic systems. And then again, for our own aero department students, I had the privilege opportunity to author a flight dynamics and control book. These two were during my sabbatical days at my other alma mater, Indian Institute of Science in Bangalore. So I was able to finish those books with their hospitality. And now, as you can see, I have a third book coming up where there's a this hopefully introduces so-called new convex stability. Right now, I have a contract with the AAA so that I can cover some of these new ideas. Okay, so what is that I have been doing in the last, let us say, a decade maybe? Let me talk about it. So that gives me a chance to introduce my startup. Please, actually, our RES was kind of happy to support American Control Conference in 2024 as a bronze sponsor, and we are proud of that. And please visit the website here, robustness.com. I encourage you to go and visit that, and there is a lot of literature we put out there. Some of them are so-called public domain, but IP protected papers. Some of them are actually not public domain, but they take the shape of a robust engineering systems technical report or something like that. So either way, these are all some new words you can first grasp. I am using the word allergic many times for many things. So first of all our algorithms in the RES toolbox are transformation allergic approach. So in a way, to contrast with our transformation compliant methods, I deliberately am using the word transformation allergic approach. The moment it is transformation allergic, we have been using phase variables a lot. But now I'm saying I'm also allergic to phase variables. I will not use phase variables. I will not use polynomials. I don't have to be bound by transformation path, transfer function path. So I'm allergic to all of it. And most importantly, tailored a power 0. So I will talk about that in more detail later on. The a power 0 definition, and then what do I mean by tailored a power 0? And in the end, static output feedback stabilization and convex stability are equivalent concepts. Therefore, maybe they can be used interchangeably. Static output feedback stabilization, which some of you may have learned in your graduate class, and convex stability are equivalent. And that in turn gives rise to this so-called distributed actuation and sensing. Basically, conceptually, it is very simple. It's information-rich, dense matrix. That's what distributed. There's no room for any zeros in the matrix in our matrix language. That's what it is, basically. Okay, so then, as usual, whatever we have been doing using eigenvalue chain, we can simply continue to do all that with our convex stability approach also, nothing different. It's just that our stability definition is kind of different. And that's why I don't expect you to read all the lines here. But all I'm saying is that we can completely embrace all these engineering disciplines and keep doing what we are doing in all your applications. And the reason I displayed this particular slide is, please be aware that there are so many different engineering disciplines which we can tackle. And whatever we have been doing with eigenvalues, we can still do the same thing with all these applications. In fact, I am urging all of you to collaborate with me, or I can collaborate with you on each of these disciplines by your own kind of platforms, robotics or automotive or anything like that. And we can continue. So suddenly, what is this so-called that allergic nature suddenly crop up? I got benefited by exposure to a non-engineering field, ecology. We'll talk about that. I got inspired by that so-called ecology principles. So before I go into why we need even this toolbox, let me first explain to you why, we need this toolbox. So first thing is that they are applicable to not just linear time invariant systems, they are applicable to linear time varying systems. And right from the beginning, we will tackle MIMO matrix-based state space systems. So that's why my emphasis is on state space right at the MIMO. So in that sense, I am not obligated to relate all these convex stability concepts to your transfer function concept. I'm not obligated, but I don't need transfer functions for that because we are attacking everything right in the MIMO matrix state space. This is actually later on I came to know in our signal processing field that Paul Swami's Stanford that method was actually MIMO antenna theory. So right in the beginning, they tackled MIMO case, and then CISO case became a special case of it. Actually, it has a lot of resemblance to that kind of Paul MIMO techniques in the signal processing area. That's why I added signal processing. Most of the applications may not be found in our standard aerospace systems. Some of the applications for RES toolbox could be found in the signal processing communication. That's why this ICON platform is an excellent platform. Again, I appreciate Martin to have included me in the speaker list because it is the kind of ICON this community that we can all put together, do something amazing. Because some of the applications are more into the signal processing area, Kalman filtering, signal processing. So therefore, and for that reason, it is also applicable to nonlinear Hessian because, as we shall see in a minute, we are starting with a sign matrix. but the sign matrix could have come from a partial differential equation or a nonlinear differential equation. And if that is the starting point, that is the reason it is applicable to even nonlinear systems as long as that sign matrix came out of a linearization, and no linearization necessary actually, a Hessian matrix. Then the most important, this is what I want you to observe. You said in your linear algebra eigenvalue theory that some system you have linear system, it is unstabilizable, uncontrollable, unobservable, undetectable. Okay, in that case, give me that system, we will stabilize our. You said unstabilizable, so but we can stabilize it. That is once some papers are coming out on that. So that is again advantage of this toolbox. Next one, yeah. So they do not suffer from blind. So we'll figure out what I mean by blind spot, non-space, real state variable divergence, and finite time instabilities. They will become clear later on. But right now, please note down some of these terms that I'm using. And this is another one. So here, because even though we don't use the transfer function concept per se, but still some kind of a ratio of output and input that's still there. But it turns out that once we come out of the pole zero jargon, it's almost like that ratio is 1. So therefore, the output always follows the input exactly, even when the output has time faster. This is a very good capability of RES toolbox algorithms, the command following. Again, there's a lot more to do, but the capability is there, and I need your help to kind of figure out whether this capability is being used, can we use it or not. And then finally, static output feedback stabilization problem was considered as one of the toughest problems to solve in the linear system theory, in many, according to many tutorials in the Automatica and other journals. So once we come out with the eigenvalue thing, we were able to solve the static output feedback stabilization. That is because right from the beginning, it is MIMO amenable with CISO as a special case. So those are the so-called features of our toolbox. And obviously, as usual, a lot of applications for each of them. And to motivate, again, all of you, of course, most of you are familiar with all these applications. And then again, as I said, ICON is a place where we can embrace all these different applications. And some of you are experts in each of these different areas. And I need your help to figure out some systems in your own area where you are having difficulties controlling it or stabilizing it. Then using convex stability idea, we can solve those problems in each of these. And that would kind of motivate you. I thought I need to come up with at least one example, one system where it can be used. I chose autonomous area vehicles because nowadays in our advanced air mobility, this so-called aerial taxis, people are saying that in the next 5 years, it will be always a reality within 5 years. So Vertical Flight Society people are working very hard to make all these autonomous air vehicles possible. But we need to be a little careful according to what the new research we have. We need to be careful about the safety aspect. So first of all, what are the challenges in this autonomous aerial vehicles? There are still a lot of challenges to place. Again, one of those challenges is that out of all the spatio-temporal scales, especially for autonomy, advanced air mobility or urban air mobility requirements is the most challenging because we are supposed to do something in a very fast time scale in a limited space. So spatial scale and a temporal scale. Therefore, here we want to do both opposite ones in a kind of that's a very challenge. In other words, in our language, inner loop and outer loop are coupled very strongly. We are tending to, using our old legacy methods, eigenvalue methods, we always use this there, oh, inner loop is more important, outer loop is separate. So we do separate analysis for outer loop designs and inner loop designs. But that's not possible for an application like this. Therefore, some of the complex applications we are encountering do need some more non-legacy methods. So that's the thing. Therefore, we cannot expect to use the same methods and try to solve these complex problems. Like that. So therefore, inner and outer coupling is very important. I guess I don't need to spend too much time on this one. We all know what are all the different risks we have in the safety, cyber security, mission. So yeah, there's no need for us to get there's no dearth of motivation for why autonomy and safety are related, especially in this application. So let me kind of go fast and then. Therefore, all I'm saying is that these new kind of complex problems require visiting where we cannot take the coupling lightly, and we need more efficient and robust modern methods for modern day data systems. Therefore, basically, okay. So then that is the so-called just a motivational. At least one application will be there where we need more intelligent and more kind of efficient algorithms. So what we have been doing all these years, why suddenly this toolbox is necessary? During my days, Martin remembers, Bob Barbish, Shankar Bhattacharya, myself, I hope included in that. We were struggling with the behavior of eigenvalues in the robust control area. Every time something kind of a literature, I mean, some kind of a integral matrix problem comes, Bob Barbish used to give a counterexample to everything people say. How is he coming up with these counterexamples? So we were wondering, what do I mean by that? So what Bob Barbish used to do is to give a counterexample to eigenvalues of the vertex matrices are all having negative real part eigenvalues, but there are always some interior parameter space. There are unstable at the center of negative real part eigenvalue stability. Always some non-negative real part eigenvalues are there for some interior parameter values. And he gave an example like this one. These are the vertex matrices. A1, this is a 4x4 matrix. A11 is varying between an upper bound and a lower bound. A4, 4. Only two parameters are varying between upper and lower bounds. Therefore, we have 4 vertex matrices. Okay, nice. 4 vertex matrices, one here, one there, one here, one there. And those 4 vertex matrices have negative real part eigenvalues. Then the question was, does a convex combination of all these polytope or hyperrectangle, do they, here it's not even a hyperrectangle, only 2 parameters, it's a rectangle. Do all the matrices inside the parameter range, do they have negative real part eigenvalues? No. There are matrices there which have non-negative real part. This is what I mean by non-convexity. Something that is happening on the outside kind of edge. They are not reproduced here in the interior of the parameter space. So therefore, this is what I mean by, I call this kind of phenomena of some interior matrices being unstable. Blind spot real state variable divergence. I call it blind spot because when Barbish produced this counterexample, we did not know why that is happening. Why that is happening? Yeah. So we struggled. And Barbish left this field. He went to finance. Shankar Bhattacharya left this field. I was there. The only guy kept on saying, why is this happening? I want to find the reason type of thing. And lo and behold, that it is due to the nature of the eigenvalues itself. It is those eigenvalues which are their behavior, the assumptions we made in the eigenvalue theory, which are resulting in this blind spot real estate variable. Another interesting thing, you know, this kind of, I call it a tumor problem. The interior tumor problem like that happens only for a 4th order matrix. That was the revelation. It doesn't happen with 2nd order, 3rd order, 4th, 5th order, all these other ones, we can see them on the edges. the instability can be seen that Cuban is spread instability inside on an edge somewhere, only two convex, two. But so they are shown in the interior very easily on the edge. That's what the so-called edge theorem by Chris Haller, they all came like that edge theorem. Only in fourth order matrix, the interior, even the edges are all negative. Even this edge, all of them are. So they are only in a fourth order matrix. So why? It turns out that what is I to the power of 4? That's the first time I to the power of I is the square root of -1. That's the first time I put up I to the power of 4 becomes 1. Right? Only fourth order matrix starts. I squared is -1. I cubed is I to the power of 4 is 1. And then you will see later on that numeral 1 plays havoc with all our eigenvalue metrics. So therefore, once we realize why that is happening, why that non-convexity is happening, then we see that our convex stability concept says all our eigenvalue methods are diagonal dominant methods. We talk about lambda I minus A determinant. Hurwitz stability, Lyapunov stability, they are all eigenvalue based exponential stability based. So why that happened only in the fourth order, and all of those things will come out because every real square matrix can be written as a diagonal component and a main anti-diagonal component. So AMD plus this main anti-diagonal will have 0 entries in the diagonal. Therefore, this is off diagonal. And starting from the fourth order, you will have some interconnection entries. These two are interconnection entries of the matrix. This is the main anti-diagonal. This is the main diagonal. This is ICT. So every real square matrix can be written as AMD plus A0 main diagonal off diagonal plus A ICT. So when you start writing a matrix A in a summation format like that, necessarily it has to be written like that. There's nothing, nobody can prevent me from seeing my A matrix to be like this. In fact, when interconnections are 0, my X matrices, X-shaped matrices can also be written like that. Then in that case, while our linear algebra books are taking A squared as simply A times A, they cannot take it as A times A. They should take A squared as A squared MD plus AMD squared plus AMD times AMD. Because in a matrix theory, AB is not equal to BA. Commutative condition is extremely important. So by taking A times A as A squared, you are completely ignoring the commutativity constraint. You cannot do that. Because even if you don't write it like that, if you write it A is equal to A string plus A cube, that you all agree that every matrix A can be written as a symmetric part and a skew symmetric. Then in that case, you put down A in this way, then also the commutativity between these two matrices has to be checked. If they don't commute, then something error is creeping into that one. If you want, you can do it. But if you ignore it, and then we can get counterexamples to the eigenvalue behavior. So therefore, that observation prompted us to say, let us get out of eigenvalues and look for a different set of indices which will not have that so-called blind spot in state variable divergence present at all. So we want to avoid that kind of a blind spot. Therefore, the only way we can avoid is to come out with eigenvalues. Don't use eigenvalues. Whenever you use eigenvalue, we can set a converse statement. Whenever you use eigenvalues, you will always have blind spot real state variable divergence. It is that if and only if it's making it like that. So therefore, let us see. So suddenly, how did we get this kind of so-called extra, so-called insight into this non-convexity problem? Fortunately, our ecology friends help us. They said, hey guys, you are talking about getting a eigenvalues of a matrix to have negative real part eigenvalues. They can do that. they consider only sign matrices. What is the beauty of qualitative sign stability from ecology? As I mentioned that qualitative sign stability result is available in 1973 by ecology and economics. Ecology in turn got inspired by economics people. Economics people also don't consider any quantitative information. They simply consider only a sign matrix, no magnitudes, only signs. But they were so, those techniques are so fascinating that, oh my God, they said, if your sign matrix is like this, simple 3 by 3, simple 3 by 3. But they said, if the sign pattern is like that, why are you taking the trouble of finding the outside criterion, see whether all those inequalities are satisfied? You don't need to do all that. Just if the sign pattern is like that, this matrix will have always negative real part eigenvalues for any magnitudes you put in those entries, leaving the zeros as they are. Put any magnitude here, and for all those magnitudes, millions of magnitudes, your A matrix will always have negative real part eigenvalues. So right there, 1973, once that theorem is available, Hurwitz criterion lost its necessity since 1970. Till 1973, yes, we did not question it. We did not know about it, actually. Eigenvalues, if a matrix has eigenvalues, the negative real part or not, we had to do the Hurwitz table and see blah, 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 and see whether it has negative real part eigenvalues or not. But now, after 1973, when this result is available, oh, it lost its necessity. I don't need to use Hurwitz criterion to figure out whether a matrix has, whether a quantitative matrix, I will call it QTS. Therefore, it lost its necessity since 1973. Okay, and then I tried to kind of, in a way, let me kind of bring your attention to, we were fascinated by qualitative sign stability theory so much that NSF said, I convinced NSF saying, there's something going on here. It's an amazing result, which will be useful to our quantitative people. Then I got a small grant from NSF, and we publicized it. We were excited about it and published the papers, but nobody cared, no citation for any of these papers. Nothing, nobody cared about it. So this is how all our QLS matrices are. These are sign matrices, whether they are QLSs or not. For example, this one here, just by looking at this matrix, this could be, no, this one will not be, it is not a QLSS matrix. This one, it is a QLSS matrix. This one, yes, it is a QLSS matrix. No, this is not. This is a negative sign. That means by looking at the sign pattern, we can tell whether that matrix will have negative real part eigenvalues, magnitude independent. But if that does not, for example, this matrix, you know why this is not a QLSS matrix? There are predated prelinks like this, and but that negative sign on the diagonal is at the wrong location. It is at the 3-3 location. But then this will not be a QLSS. Therefore, that sign pattern matrix will never be qualitative sign stable. You have to use Hurwitz criterion to know whether it has, for those magnitudes you put in those, whether it has negative real part eigenvalues. So therefore, that is how great they are. Look at the beautiful names they gave. All our plus minus off diagonal predated play interactions. All our plus plus signs, mutualism. Minus minus in the off diagonal, competition. That means, you remember, symmetric matrix has plus plus and minus minus. And what does our eigenvalues do? They don't differentiate between plus plus and minus minus. The eigenvalues will be the same, both for plus plus signs and minus minus signs. So we'll call that later on sign pattern. But most important interactions nobody kind of knew is that emmensurism and commensurism. -0 is emmensurism. Why? Why this is important for us? We guys simply multiply something, but when something is 0 multiplication, we don't know what the other element is. A12, A21 is 0. But A21 can be 0, A12 can be extremely large, but still the product is 0. But whereas these people are saying, no, there is a difference between minus zeros interaction and plus zero interaction. And we can solve that according to ecology, anything plus has a diverging, anything minus converge. So beautiful, conceptual, qualitative kind of saying that. Therefore, the moment this kind of thing came up, then I now see every matrix, how many positive sign elements are there, how many negative sign elements are there, how many zeros are there. Oh, if the number of positive sign elements is much more than that matrix will never be. Will never be Hurwitz. That's how great. Okay. And within the QLSS matrices, that's why something is handwritten here. Last minute I said. Within the QLSS matrices, we can also distinguish between weak QLS and strong QLSS. What do I mean by that? This matrix is a QLSS matrix, as you, I mean, you may not know it, but we can say that because three related, and even though there is a mutualism, but the product is zero, therefore, still because the product is zero, this still has negative real part eigenvalues. But look at only one negative diagonal element. So even that one negative diagonal element is giving you the kind of property that it will have negative real part eigenvalues as long as all the other off diagonal elements are predator prey. But this so-called only one negative, which is something like equivalent to our trace. Therefore, the trace is very weak. You have weak negative real part eigenvalue. That means your negative real part eigenvalue real part will be extremely small compared to the imaginary part of it. See how beautifully that is already kind of known beforehand that that is a weak QLS. Whereas this one, so you can look at how many negative sign elements are there. This is a strong QLS. This is also has negative real part eigenvalue, but its negative real part eigenvalues will have large real parts negative and then small negative. So therefore, and then I'm calling all those matrices where we can put our own magnitudes and then convert a sign matrix into a quantitative sign matrix. So I'll call them QTS matrices. So if you put some kind of, for example, here, yeah, we put some magnitudes of our own. But once you see that is a QLSS sign pattern, whatever magnitudes you put, it will be having negative real part of it. The moment you change the sign, look at this one. I changed the sign, only one element, and then maybe this one. Yeah, this one. See, the moment I changed the sign of one half diagonal element and one diagonal element, this is no more a qualitative sign still. This one you have to use browser criterion to see whether it has negative real part eigenvalues or not for those magnitudes. You see? So therefore, that's how useful. And now if sign patterns are becoming the starting point of our analysis, then even a simple 2x2 matrix has 81 sign patterns. And a 3x3 has this many sign patterns. A 4x4 matrix has this 43 million sign patterns. And a fifth order matrix has this many. Then you may be asking just now, do you want us to kind of look into all those big matrices, so many sign matrices? No, you don't have to. You need, however many sign patterns are there are still three kind of important sign matrices, single sign matrices. We'll come to that in a minute. All plus, all minus, all zero. Only those three matrices matter. Nothing else matters. So those quantitative. And these quantitative matrices are not accessible to our linear algebra methods. Linear algebra methods are constrained by the relation that A is equal to A sim plus A skew sim. Yeah.
How do you get 81 sign patterns in a 2x2 matrix?
There are three elements, right? 0 plus 3, and then each one has 4 elements are there. 4 times 2. Oh, yeah. So therefore, yeah, I will show you some of the matrices. So therefore, like that. The number of sign patterns goes crazy. But some of those QTS matrices are invisible to our TC methods, LA methods. They cannot. So therefore, in other words, our so-called QTS matrices are working with your data-driven. There's millions of matrices out there which are not accessible. That's why we were able to get counterexamples to use those invisible matrices for the eigenvalue methods, LI methods. We use those to get counterexamples to every statement made. So therefore, what we have done, in RES toolbox is we combine the 100-year-old DC methods. This is what I mean by saying transformation component, linear algebra, MATLAB methods. Those are all. And PLSS methods are sincere. So then now I am saying because of QLSS theory, sign pattern theory, Rutherford criterion lost its necessity. Now, because of our convex stability theory, transformation analogy, PV and CF, Rutherford criterion loses its sufficiency also. So therefore, in a way, negative real part eigenvalues criteria. This is a strong so-called provocative statement I am making. Negative real part eigenvalue matrices are neither necessary, negative real part eigenvalue condition is neither necessary nor sufficient for the stability of a linear dynamics. That's kind of a little, it shocked many of us later on. And the side benefit out of PLSS theory, what's the TIU? Now I can tell you, just as ecology people gave, by looking at the sign pattern, we can tell you whether that matrix has negative real part eigenvalues or not. Then RES is saying, by the same token, I can now give you, by looking at the sign pattern matrix, whether that matrix will never have negative real part eigenvalues or not. I can tell you. So that's a lot of computation reduction. You don't even have to check to see whether that matrix has negative real part eigenvalues. You don't even have to use Rutherford criterion at all. Just by looking at that, I'm calling it transformation analogy. Already, it will never have negative real part eigenvalue. So therefore, that means this is independent of the magnitudes. No need for eigenvalue. So let me actually go first. So therefore, So now, why did it lose sufficiency also? Because based on the invisible many matrices that are not accessible to LI methods, we picked those matrices to come up with a counterexample to every statement made in the linear algebra. But so therefore, here is the punchline. TC, LA, MATLAB eigenvalues are commutativity ignored. What do I mean by that? A squared cannot be taken as A times A, and we are neglecting we are not looking at the commutativity concept. So they are not only ignoring, they are violating. Then all the eigenvalues you see in the MATLAB outputs, they are wrong quadrant. Why? Because they are using LHP, RHP based. That only the first quadrant, both are positive. That means they are using sin squared theta plus cos squared theta, one property. But even when they use it, sin theta lies in the second quadrant, cos theta lies in the fourth quadrant. Therefore, even when they use it, they should have had opposite quadrants for a side face. When face is 0, they should add up to a 0. Only that happens when the eigenvalue complex convex pair is in the second and fourth opposite quadrants. But we are saying RES is saying the same one, numerical one, can also be secant squared theta minus tan squared theta. So why can't we use that for the same one? Why should I always use only that? But once we start using that, we can see that that small angle approximation we use in the LA theory, the angle is considered to be small if sin theta is equal to theta. That's what we say. Now I am saying, again, RES is saying, no, right? The small angle approximation is valid only when sin theta is very much close to tan theta. So sin theta and tan theta, if they are close to each other, then also that is the actual small angle approximation. So non-convex, we saw that. Therefore, we look at the list of the why these are all their eigenvalues, the matter of eigenvalues that are commutative ignoring, commutative violating, wrong quadrant, non-convex, sign pattern blind, as I said. They give the same eigenvalues for both symmetric matrices with plus sign and minus sign. What is that? There is no difference between ecology people told us that plus is a divergence property, minus is a convergence property. So you are not making use of that. You are not distinguishing between plus and minus. Then matrix data blind. Why is that I am saying? What do we say for upper triangular matrix? For an upper triangular matrix, what are the eigenvalues? The diagonal elements themselves are the eigenvalues, right? You are saying. So do you mean to say that all the upper triangular elements that are staying in the upper triangular, they are useless for you? No, they cannot be useless. They can overpower your diagonal. If they're all plus signs, only the diagonal is negative. All those plus signs will overpower your diagonals and then come up with a counterexample to eigenvalue variance. We'll see. Yes. Okay. Matrix order blind. Matrix order blind. Yeah, did you ever say any of the matrix properties we say, lambda, that eigenvalues of A are same as eigenvalues of A transpose? Did you ever say what is the nature of that matrix? Is it an even order matrix or is it an odd order matrix? It very much depends on that. But our statements never made a distinction between matrix order. They never distinguish between even order. One size fits all. Here is one. A power 0 is taken as an identity matrix without even caring about the element of sign. How can that be? For example, suppose you have a matrix with non-sparse entries. That means in our language, giving respect for ecology people, I want to use I don't want to use non-sparse. I want to use the word omnivorous matrices. So how can A power 0 be only identity matrix for an omnivorous non-sparse matrix? That doesn't make sense to me. Similarly, for a skew symmetric matrix, which always has 0 diagonals, how can A power 0 be identity matrix for that? I don't see any logic in that. So, and concurrent 3-field scalar. Eigenvalues can be real, they can be complex conjugate pairs, they can be pure imaginary, and in a particular 6th order matrix or large order matrix, they can all be combined together. So 3 fields, real field, pure imaginary field, complex field. Eigenvalues will be simultaneously spanning all these 3 fields. Then that's the reason actually you get oscillations and other things. So finally, situational unaware. What do I mean by that? No care taken to know a priori for what purpose that matrix A is being used. Is it being used for y equal to ax? Is it being used for a continuous time dynamic system? X dot equals that should x dot. X dot equals ACX. Differential equations. Is it being used for a pure discrete time system? Xk plus 1 is equal to AD This AD matrix is different from AC matrix, strictly speaking, because in a pure discrete time system, AD can be ADF or ADB, backward difference or forward difference. So within AD, there can be ADF and ADB, but no distinction between is this A, is this the A, is this the A, is this, and sample data system, xk plus 1t is equal to g xkt, where g itself is e power ACT. You are using the same ACT matrix in the G matrix for the sample data system. Sample data systems are a very crazy combination of discrete and continuous. G power ACT is becoming the plant matrix for a sample data system. But if the constant sampling period is there, when capital T is equal to 1, G is e power AC. But we use that one here also, x dot equals AC. We'll talk about that, and then we don't have time here to see why. And finally, actually a simple reason I can give you for why all of this is unnecessary is that the lambda plus A cannot be equated to a real 0 when lambda is a complex variable, because that's a real scalar. How can it be equated to 0 when lambda is complex? Lambda is sigma plus I omega. So how can sigma plus I omega plus A can be equated to 0. That 0 cannot be real 0. It has to be a complex 0. Sigma plus A can be equated to real 0, but not lambda plus A. So therefore, then lambda plus A whole square cannot be equated to real 0. Therefore, you have to necessarily use a complex 0 on the right-hand side to make lambda as a complex variable. So a real variable quadratic equation roots can never be equivalent to 2 eigenvalues of a second order. Some of the statements I'm making here bothered many of my peers in the control theory. But slowly, there was a lot of resistance to some of the statements I made here. Many papers were rejected, but I insisted because I have a logic here. And in the end, recently, papers are getting accepted after they listen to. So therefore, our MATLAB routines R is equal to root speed. Many of you should be using R is equal to root speed command. They don't make any distinction between whether that P vector, P transpose vector, is it a real variable coefficient polynomial or a complex variable coefficient? We'll talk a lot about it in the papers. Right now, I don't have time to elaborate on it. So in the end, one final blow. Contrary to what they said eigenvalues are invariant under linear non-singular transformation. But I am saying eigenvalues are variant under, I don't call them similarity transformations, I call them non-similarity transformations. Let me give you an example right here. This very carefully crafted matrix A, very carefully crafted matrix, what I call Z. So this is the A matrix. Look at that one. The A is 1 over 6 to the power of 5 once. So I call it more like a Jordan matrix. But the eigenvalues of this, according to your own LA methods, their eigenvalues are the diagonal. This is an upper triangular matrix. So the eigenvalues are simply real. Yeah, whatever that A. Now I will build a user fabricated matrix Z. Look at that matrix very carefully. Minus A is also inside the Z. And these B's are especially selected magnitudes. And they are all here. And you do the AZ left and AZ right. Z inverse AZ, A inverse AZ in. There's a difference between Z inverse AZ or ZAZ inverse. I call it AZ left, AZ right. So right now, AZ left eigenvalues are like this. These are supposed to be the eigenvalues of A, right? But these are the transformed eigenvalues. I even see positive real part eigenvalues, while these are the eigenvalues of A. That is AZ left. Now let us look at AZ right. Look at AZ right. Again, positive real part. So not only that the eigenvalues of AZL and AZ are different from the eigenvalues of A, the eigenvalues of AZL and AZR are opposite sign eigenvalues. These are all unstable matrices. This is supposed to be a stable matrix. So I'll give you 1 minute to absorb. This is a statement everybody is saying. How the heck did you come up with that? Okay, so therefore, enough of this. Okay, let me kind of quickly say a unit circle matrix. Yeah, so that what does that all mean? Unit circle matrices can be come to 0, but unit square matrices cannot. Let me give you, yeah. So that alpha, there's a unit square matrix. That means off diagonal elements are playing a big role. Unit circle matrix is only diagonal elements. It will stop at that. There's an Argand barricading square, so it will never reach asymptotic stability. And that so-called direction is not only when shrinking area, it is also happening in the enlargement area. Then also it gets barricaded by. So therefore, this is what I mean by finite time instability in the steady state direction finite instability state is finite instability in the transient direction. The small square is the transient direction. This big square is the steady state direction. So therefore, all these, therefore, we simply say, let us not use eigenvalues with so many different behaviors like that. Let us simply get out of eigenvalues and come up with a new thing that is convex stability. So convex stability is basically, I'm almost done, nested stability. And so the big message I want to give you is, don't underestimate second order matrices. Everybody says, oh, it's only a second order matrix. What can it do for me? No, it's not good here. Second order matrices are the building block for all the convex stability of all the higher order matrices, because every higher order matrix will have A11, A1n, AN1, ANn. It's always built with the second order matrix. Therefore, second order matrix becomes most pivotal matrix in any convex stability. Right? Therefore, in the end, what is convex stability? I want your without using eigenvalues, I want your closed system matrix to have all negative entries. So this is the convex stability. That's why I said in the 5 minutes back, even though we have millions of sign patterns, in the end, these three, what is the third one? Zero, all zero. I didn't put it here. So, and if you go to MATLAB and then give all positive element, even a 3 by 3, you will see a negative real part complex conjugate pair. How can we have a negative real part complex conjugate pair for an all positive diagonal matrix? So that itself should convince you that eigenvalues have some trouble. All matrices are positive. So how can you have negative real part complex conjugate pair? So that is a proof that there's something wrong with the way the eigenvalues are displayed. They are wrong quadrant eigenvalues. So in the end, we can actually talk about magnitude independent convex stability, magnitude dependent convex stability. So this one here, having all negative entries, is a magnitude independent convex stability with a little small adjustment where these two can be plus. We'll call that magnitude dependent convex stability. Those are coming up later on in the papers. So by the way, all of this discussion over the last 2 years have been in the public domain with IP protection, and I'll keep it here for a while, but it's being recorded here. So you can access all of these by Googling my name, and then hopefully these papers will come out. I'll give you, at least I want you to read. Most of them are ACC 24, some are IFAC, some is Big Sky ITD Aerospace. That is in 2024. And recently, I'm most happy with the publication of my papers in 2025, where look at the titles of the papers. Currently, PID control is not sufficient for convex stability without using eigenvalue. And convex stability and distributed. So what is this distributed actuation sensing? Yeah, just as you can see, every matrix is all dense, no zeros. So distributed actuation. It's always distributed all over the that we'll kind of figure out. I don't have time to. Yeah, so therefore, this is the MECC just recently in Pittsburgh. So Hurwitz stability and Schur cannot coexist according to our. Convex stability condition does not need determined. Then here it is. So it is published in MECC, Pittsburgh conference. Counterexample to the concentrated matrix is lambda I left K. This is a linearity property, but I can give you a K and a special A such that this property is violated. That is the paper. And then again, for controlling acceleration, again, PID controller is not certain. So majority of them statements I made here are extremely provocative, I agree. But I gave you the reason. I told you why that is happening. a little bit knowledge about qualitative sign stability would have helped us, but we never cared. So, to conclude, I'm almost done. So, therefore, please encourage your therefore, I'm not now that what I'm saying. So, don't treat quantitative methods against qualitative methods. Both are important as long as we carve out a nice intersection. So, all I'm saying is both are important, but time has come to figure out how to carefully blend these two viewpoints together. That's all I'm saying. Then, as I said, once I didn't use eigenvalues, we were able to solve the static output feedback theory. That was in general ACC 2024. Now, the general case is getting there. So, therefore, in the end, all our convex stability methods are eigenvalueless and inversionless. So, therefore, some of our signal processing people told me, so they said, hey, your aggregators can be useful for our so-called wireless wireless communication. Right? So please recommend our toolbox to your authorities in Purdue. And then as a professor, I'll be happy to collaborate with you guys. And again, as I told you, some of those instabilities, you cannot see fortunately in a big aircraft or maybe even drone possible. But most of the instabilities I talked about, unseen, invisible to TC methods, is in the power electronics and communication. I can see the chip, integrated chip burning if too much computation is there. People said that, therefore, I'll stop here and take some. Just note down please, again, I'm distributing a flyer. Feel free to take them so that you can communicate with me on these emails. I'll be happy to send them. And again, I urge ICON to make me a part of your collaborative research efforts. Together, we can do a lot of things, new things, and solve a lot of, again, as I said, the reason I get excited, and then I'm saying some of the statements in a very, maybe kind of a tone you may not like, is that it's not, I'm not getting excited to say that, oh, eigenvalues are kind of useless. No, I'm not saying that. I'm simply saying there's a new door we opened. We just let us go through that new door. Enough of these old legacy methods. Let us embark on some new methods which are needed to solve complex problems. And so, yeah, let us use our God-given brains to make some things happen. Thank you. I know you have a lot of questions. I have a lot of backup slides. If fortunately one of the backup slides serves the purpose, I'll be happy to use it. But feel free to shoot your questions. It will take a little while for you to. I know. Yeah.
But if any system is controlled then how do you use the sign stability concept?
I'm talking about continuous time system.
Yeah, any continuous
Statical ACS.
plus
Video, sure.
then so you use like page
Right. So we could design a controller. Suppose ACB is uncontrollable, unstabilizable, blah blah blah. Because you are looking at the AC eigenvalues. They are coming up. So I'm simply saying for a kind of ACB case, which is uncontrollable, unstable, give me that, and then we can convex stability controller this area. By using, because I'm not obligated to go through your transfer function. So my ABC triple is independent of your ABC triple coming out of your realization. We are using to getting a transfer function, and then A matrix is coming out of that. Yeah, ABC are coming out of that. I said, no, I will use my own, the given AC, which has all the sign pattern information. And then this distributed actuation and sensing is I will use my B and C as designing matrices because I have control over it. That's why. So I will stabilize something you said it unstabilized. That paper is coming up with you. The next is you are 26. That's yeah, sure. That's a good question. Yeah.
You said that. All the eigenvalues in there, say have a negative big parts is not necessarily sufficient for stability. You have any time?
The examples are, yeah, I mean, they are, in a way, those are examples, which are counter examples to some of the eigenvalues. So that means that statement is wrong, or I mean, is incorrect, is corroborated by the counter examples we are able to produce for the eigenvalue problem.
Yeah, but you have a specific matrix that illustrates.
Those will be there in some of those papers, or we can come up with the. I know,
Okay, please talk. So maybe I think I'll have would like to see the specific example like the Martin mentioned. Maybe I think we might have some confusion. That means we are talking maybe some misunderstanding and in terms of certain concept, right? So
basically,
yes, I see the example you show here, right? To me, you are saying that okay, you got some of those eight metrics,
Right.
and you're showing that MATLAB give you wrong eigenvalues. But from me, I was saying there's nothing wrong with the theory. It's just how we calculate eigenvalues numerically.
It's numerical.
It's the numerical issue. It's because the only numerical issue does it like when any kind of computer. When we define theory, we define zero. We know precisely what it means. But when you just do the numerical calculations, and then computer will never say what's zero, what's
very good point. Very good point. So that's what that is where that so-called all plus sign thing comes into picture.
yeah.
So,
So now I understand. So I don't know. Maybe we have done this, but I say we don't want to say that theory-wise everything is perfect.
Okay.
It just say that's the problem is there. Now that's give us student a very good. Don't ever trust numerically. Any simulation. That's why we have to develop theory because when logic is correct, it's correct. It's not anything. Otherwise, we always something. It means that we have to double check that.
Yeah, I am simply saying. So, but that so-called all plus matrix. That matrix, you are routinely calculating eigenvalues for that matrix. You read that one, then MATLAB will give us some eigenvalues. You are saying there's nothing wrong with that.
No. See one thing.
Right.
For most cases, right? Unless we get into those very numerical ill condition, most cases the calculation is reliable. But you we have actually very specific, diagonal, very small, of that very. And typically that's a ill condition so we have to make us say if you just purely with the student, right? You want to care, you just rely on what's coming out of the software. Then what I'm saying that we never trust that one, but theoretical analysis. Why you can handle that? Because for me, as you look at you touch science stability, you're really talking about robust stability to parameters unknown the whole entire arc. So that's very you obviously if you can achieve that, it's very it's very just definitely there's no numerical issues there. You know that's how to say you see any word you can probably guarantee that whatever you're designing that. But then for me to say but it also has a shortcoming to say well you are dealing with a very and not just that's robust so rich too much. Your design is going to be very conservative. So I'm not saying that you're wrong. So that's about can not some of these.
All your statements are validated. They are all brought up in the paper reviews. We are answering them. We answered them actually. That we kind of there. So the big difference between the so-called proponents of eigenvalue methods is that you gave me a matrix A. So, as you can see right from the entire part, I am giving a lot of importance to the moment you give me a matrix A. I will spend 5 minutes looking at the elemental sign and magnitude structure of that matrix. I will spend 5 minutes and then decide whether we should compute eigenvalues for that matrix or not.
Yeah,
Whether the eigenvalues given by for that matrix are making sense or not. So, therefore, having said that, even if you take a skew symmetric matrix with all diagonal zeros and off diagonal elements, whatever they are, in fact, whatever their magnitudes are, how can the a power 0 of that matrix be taken as identity matrix is required? Therefore, don't get into computing eigenvalues immediately. Look at that matrix for 2 milliseconds. Then my question to you is, how can the a power 0 of a omnivorous matrix with no zero, how can that be identity matrix? It should be loop matrix, all once. So first spend 1 minute looking at the matrix you have in front of you.
Okay.
So
Yeah.
I simply disagree that without looking at the A matrix elements, you are immediately computing eigenvalues for that. I swear, no. Because that matrix, the elemental sign structure and magnitude structure could be such that it will not get good eigenvalues. Eigenvalue definition of thought.
So, okay. Yeah, that. We'll probably have to say, yeah, look at this, one say. Why you have got any, not A, 0, you got I, right? Just like we define, divide all this matter of theory, right? Just see. You start with some, just anything, right? Start with certain, basic, just whatever the rules you set up, right? If you, it's only define, any matrix to 0, then you can define it was E minus Y. Because we know about multiplication, we define E squared equal to A times A. Yeah, and so I'm not really confusing about why that definition is not right.
I thought that if I see a matrix given to me, I will
Yeah.
start writing it as A and B plus A0, and I will start.
Yeah, you can't, yeah,
And that's
that
square.
doesn't matter.
So therefore, okay, to answer your question, let me give you an example where do you agree that any A square matrix, even if you write the linear algebra way, do you agree that when you make an A square matrix, the diagonal elements and the off diagonal elements are getting connected, and then there will be a structure to the A square matrix.
Yes,
Right?
Uh-huh.
Do you agree?
Yeah.
Therefore, diagonal elements and off diagonal elements are getting connected to that one. And you will get a square matrix in an analytical way for a 2 by 2 way. Even for 3 by 3, you can get an analytical way. So that matrix has diagonal elements and off diagonal elements inside it.
Yeah.
So what I am doing without you knowing is that I can select my A11, A1, A22, A33, A1, all those elements very carefully with different signs, magnitudes, such that your A square matrix will have 0 diagonal. I will select entries in the
Yeah, that would be very interesting.
I will put a simple example where, in other words, I'm simply saying, I will select elements in such a way that, see, what I have control over my elements.
Yeah.
LA methods don't have control over their elements. They are constrained by the fact that A has to be equal to A symmetric. Whereas I am, that's what the difference between LA matrices and QTS matrix. In a QTS matrix, I have the ability to separate out. I have the ability to separate them out. And because of the ability to separate them out, I am seeing millions of matrices there. But TCLA methods cannot see millions of matrices. They are constrained and they are dealing with only, I can give you the number. Suppose you take a 3 by 3 matrix. Then they are dealing with only I actually see the number right there, maybe about 100 matrices. Whereas I am seeing 19,683 matrices for a 3x3 matrix. They are seeing only 100 matrices. Because I decoupled in the few case matrices, we have the provision to separate out main diagonal elements from the off diagonal elements and the interconnection elements in 4x4. So that ability to separate them out is giving me access to many ways.
Oh, yeah.
So in the
So-
interest of time, I think we'll call the seminar there. Thank you so much, Rama. Yeah. Thanks very much. And Rama is here in case anybody has further questions.